DACs are extensively used in control loops to position actuators or control valves, and this is an area of closed-loop control where the DAC is continuously changing its output in response to changes in the system. This is in contrast to the first two areas where the DAC could potentially be used in a set-and-forget configuration. That is, once the optimum output is determined, the DAC code is set and then remains unchanged for the duration of the system's life or a given power-on period. Positioning and control loops are one of most popular applications for DACs nowadays. In this example, the DAC sends a voltage command signal to a transducer, which in this case is an actuator or positioner. This command signal generates a change in the physical parameter of the transducer. An actuator is usually activated by a low-level command signal, so an amplifier may be required to provide sufficient power to drive the actuator. Actuators are often biased at 0 volt to provide better reliability over time. They also require bipolar swings to excite them, as this allows motion in both the positive and negative directions. There are effectively two types of common control loops, open loop and closed loop. For open loop control, there is no feedback, so when you move the actuator, you effectively assume it is in the correct position. Here, the accuracy of the DAC is important. In closed loop control, as shown here, there is a feedback network. Closed loop systems are ones where a feedback path exists from the sensor. A sensor monitors the output from a physical parameter such as servo motor, flow valve, or temperature sensing element. The sensor output parameter is monitored and communicated back to the processor for analysis versus the preset output. The processor then determines if correction is required. A DAC is used in the feed-forward path to make adjustments to the system, and an ADC is used in the feedback path to monitor the effect of those adjustments. Together, they force and sense the analog control signals to make real-world adjustments to the parameter they are controlling. Open loop is typically used for applications like opening and closing valves, where there are two fixed positions, whereas closed loop control is used for valve positioning where there is a need to adjust flow rate. The accuracy of the DAC in terms of INL is more significantly in open loop systems, as there is no feedback. Since the DAC is in the feed-forward path in closed-loop systems, its integral nonlinearity INL error automatically compensated for by the feedback path, so it is not a key specification. The DAC, however, must have good differential nonlinearity DNL and be monotonic, that is, to have a DNL of 1 LSB or less. Another example of a closed-loop system is a motor controller module. The DAC is used to set the motor rotation speed and direction. The desired output or set point, equivalent to the desired motor speed and direction, is set by the DAC and is then applied to the motor driver network. A bipolar signal is required here to set the positive and negative direction, reason why bipolar DACs are preferable. If an LVSS DAC is used, then an amplifier is needed to change the signal to bipolar. The microcontroller will adjust the input code to the DAC, which then produces the required analog voltage as an input to the motor driver network. The DAC output voltage is then amplified through the driver network to provide the required driver current to the motor. Not shown on the slide is the microprocessor controller, which determines the speed required and will take the feedback from the feedback network. It should be noted that the DAC can be some distance from the motor, and the output can travel across long cables with capacitive and resistive loads before reaching the driver network. These cables may cause voltage drops that will need compensation. Here, the V-Sense features on some of the industrial DACs like the 8542 would be useful, as it enables the detection and compensation for series resistance. Let's summarize now what type of DACs are best for position and control in control loop systems. As noted, bipolar DACs are often ideal in these applications as they provide bipolar swings of ±10 volt, ±5 volt, and enable biasing at 0 volt, which is often required for actuator or sensor biasing. There is an extensive portfolio of single and quad bipolar DACs with flexible ranges, which could make a nice option in these applications. Nano DACs can be used here, and if the negative voltage swings are needed, additional buffering can be used to generate the required ranges. What is important in this application? For the majority of applications, 12 bits is sufficient, but there is a trend towards 16-bit resolution for more precise control. As mentioned earlier, INL accuracy of 8 to 16 LSBs is sufficient, as the feedback will compensate for any accuracy error. Temperature drift is an important specification to note, as any drift in the electronics will create an error in the positioning of the transducer. An important specification to highlight is TUE, the total unadjusted error, which is specified to include the full drift over the specified temperature range. TUE is a measure of the output error taking all the various errors into account, including INL, offset, gain, temperature, and time. In this application, the DAC signal effectively drives a motor, moves a solenoid, or adjusts a valve. Solenoids and motors are inductive and can have energy stored in their coils. This becomes significant when calculating the stress on the output driving circuitry, so buffering of the DAC is needed. Actuators, motors, solenoids have varying load characteristics from inductive or capacitive to resistive. The type of load will dictate the current drive requirement from the output circuitry, and this is what dictates the use of additional amplification circuitry or buffering, as highlighted in some of the examples earlier.